So, I'd like to welcome you all here to Trung Nguyen's PhD defense. Trung has been with us for a while. It doesn't seem that long, but it's longer than it seems like sometimes. So he came originally as a Fulbright fellow and as part of the IGERT bioenergy NSF interdisciplinary research education training grant that started up that John Field is also a graduate of. But so Trung came in the fall of 2001. Was here, went through the IGERT. 2001. Not that old. You caught me out. All right. I knew there was a 1 in there somewhere, but anyway. And then after a couple of years of that, then Trung was part of the IGERT's program was to have an internship to come and work in industry or somewhere, and normally students would go out for a couple of months. Trung went down to Shell with Christian Davies, who's on his committee here, and ended up staying at Shell in Houston for 14 months. So he took a little bit of break off, but I think that was really a very valuable part of his education. He got exposed to a whole lot of other kinds of ideas, and I think a lot of that, the combination really of the time at the IGERT and the subsequent time here at CSU, as well as the experience he had at Shell, has kind of come together and produced, I think, a very interesting amalgam of what his dissertation is about, which is integrated assessments of agricultural ecosystems using simulation, optimization, and machine learning. So, Trung, please take it away and tell us all the cool stuff you've been doing.
Thank you. Yeah, I'll just pop that up so I can keep track of time. All right, thank you everyone for coming to my dissertation defense today. I've been working on this for so long and really excited to share with you some of the results. My dissertation is about integrated assessment of agriculture ecosystems using simulation, optimization, and machine learning. It's a big name. So as we all know that agricultural and land use activity contribute 24% of global anthropogenic greenhouse gas emissions. Although agriculture provides many foods and products to sustain the world population of 7 billion people, it's also the main driving force of deforestation, biodiversity loss, soil degradation, and pollution. It accounts for 70% of global freshwater withdrawal. And the impact of agriculture on the ecosystem will likely to increase in the future with ongoing population growth. The world population is projected to be 9.7 billion people in 2050, and that will likely result in 70% of 8 to 85% increase in the demand for food crops, and 30 to 85% increase in water demand over the next 5 decades. In addition, the production and use of biofuels for energy security will impose further pressure on agriculture. Meeting the increasing demand for land, water, food, and energy will require more efficient use of natural resources to maximize productions at the minimal cost on the ecosystem. That, in turn, will need integrated assessment method as well as decision support tool to facilitate thorough analysis of agricultural production system. My dissertation focuses on developing the methodology and tools to support decision making in agricultural ecosystem. For this, several frameworks and methodology and tools were integrated into a modeling platform called the Ag EcoSoft. Now I'll go right into explaining some of the main methods and frameworks that I use for my dissertation. To guide the method and model development, I used the Millennium Ecosystem Assessment Conceptual Framework. This framework was prepared by over 1,300 scientists from 95 countries, and it provides a foundation for holistic research approaches where multiple perspectives are integrated to assess the impact of decision-making and policy on ecosystem sustainability and eventually on human well-being. This framework emphasizes the linkages among drivers of ecosystem change, ecosystem services, and human well-being at multiple geographical and time scale. Now, ecosystem services are defined as the benefits that humans obtain from the ecosystem and are often classified into 4 main categories, including supporting things like nutrient and water cycling, provisioning like food, biomass, and fresh water, and regulating like climate regulation, pollination, and cultural services like recreation and aesthetic values. In order to quantify ecosystem services, I use process-based biophysical models. These models utilize a set of input variables such as soil and weather condition, cropping practices, and produce a set of output variables like dry matter, so organic carbon, that describe the ecosystem states and functions. When coupled with Geographical Information System, GIS, this model can quantify ecosystem services at multiple spatial and temporal resolutions. This provides continuous feedback between decision-making and ecosystem response. In my dissertation, I used the DaySen model, and it's a monthly time-step version century model to quantify changes in ecosystem services induced by changes in management decision. Several model outputs were used as indicators representing different ecosystem services, such as grain for food production, harvested biomass for biomass production, and so on. Now, I noticed that there's a lot of DaySen gurus here, but for some of you who are not familiar with the DaySen, here is an overly simplified diagram of the DaySen. First, it is a biogeochemical model, so it simulates the cycling of carbon, nitrogen, water, and other elements among the atmosphere, vegetation, and soil. Secondly, it's a daily time-step version, so it operates on daily basis, utilize size-specific and management-specific inputs, and produces ecosystem outputs like trace gas fluxes, yield, and so organic matter. The model has been developed for over 30 years and has been widely tested for a variety of US agricultural systems. It's also used in the national greenhouse gas inventories. So I guess it's pretty good, right? If you have not used it, you should. It's fun. Let's get back to the modeling framework. Process-based models are useful, but they can be slow for large-scale analysis. And so machine learning was used to create simplified models of the process-based models, aka meta model or surrogate models. These models are typically faster and less expertise driven. In a nutshell, machine learning is the automation of analytical model building by giving computer systems the ability to learn information directly from data without relying on any predetermined equation as a model. As an ag person, I like to think about it by analogy with plant growing. For this, nutrients are data, seed is the machine learning algorithm, and plant is the analytical model. So you feed the seed with nutrients, it will grow into a plant. Same thing go with machine learning. The artificial neural networks were employed in my dissertation to create simplified model of the DaySen model. To evaluate the impact of decision making on ecosystem service provision, I used life cycle assessment, LCA. LCA is studies of environmental aspects and potential impacts throughout the entire life cycle of a product, from raw material extraction, product manufacturing to use and disposal. The purpose of an LCA is to compare between different products, processes, or services, or to identify parts of the life cycle where the greatest improvement can be made. An LCA is typically carried out in 4 main phases, as shown here. The final step is to optimize our management decision making so that we can maximize ecosystem service provision while minimizing the impact on ecosystem. Optimization will also allow us to quantify potential trade-off between different management options, as well as to identify the most efficient configuration of agricultural landscape. This concept is pretty important because most of my results will presented in this presentation will be based on it. So optimization. It is finding the best solution for some problems given a specific objective function and a defined domain, like input constraint. When more than one objective function is considered, the problem becomes multi-objective optimization. The trade-off is created when these objectives conflict with each other. And this is often the case of modern agricultural production, when multiple competing objectives like food and biomass production, water quality improvement, climate change mitigation need to be considered at the same time. A multi-objective optimization typically generates a set of Pareto optimal solution, where any improvement in one objective will always impair some others. Meaning at that stage, one cannot get any better on one objective without sacrificing at least one other objective. The collection of all the Pareto optimal solution is known as the Pareto frontier, showing the most efficient trade-off between the 2 objectives. Optimization of more than 2 objectives will generate a Pareto surface. Several optimization algorithms were employed in my dissertation. Now, there's a lot of interesting results that can be inferred from this type of analysis, but in this presentation, I will only focus on identifying or discussing the extreme region associated with these trade-offs. These are the regions where a small improvement on one objective will lead to huge deterioration on other objectives. And although they are optimal, they should be avoided, not favorable. Okay, so those are really quick summarize of all boring concept. Now let's jump right into some more interesting research findings. My dissertation is structured as 4 independent case studies highlighting different aspects of model development. The first case study here linked century models with life cycle assessment to explore the impact of changes in ecosystem carbon stock associated with cassava cultivation for ethanol production in 4 main cassava growing regions in Vietnam. The second case study developed the Ag EcoSoft and used it for a trade-off analysis of ecosystem services for irrigated corn growing area in South Platte River Basin, Colorado. The third case study integrated LCA into the Ag EcoSoft for a life cycle-based optimization of feedstock landscape design for a hybrid ethanol production system at the Front Range Energy Biorefinery, Windsor, Colorado. And the last case studies developed a surrogate-based optimization framework for the Ag EcoSoft and used it to explore the trade-off among 7 management objectives for the irrigated corn growing area in the whole eastern Colorado. The color themes here will be used throughout my presentation to separate between studies. Here's the first case study: impact of ecosystem carbon stock change on greenhouse gas emissions and carbon backbarriers for cassava-based ethanol in Vietnam. Cassava has been considered as a potential feedstock for ethanol production in Vietnam and many other parts of Asia, including China and Thailand. LCA studies have been conducted to assess the environmental performance of cassava-based ethanol in the region. However, as you can see here, the results vary greatly. There are 2 main reasons for that. The first one is differences in study assumptions, and another big one is the lack of consideration of the emissions from land use change due to cassava production for biofuel. The study that included these emissions used the estimates, tier 1 estimates from the IPCC guideline to estimate changes in soil carbon stock due to generic changes in land use type. This approach, while fast and convenient to do, is poorly suited for quantifying the effects of locally impacts on soil carbon stock change, things like soil and weather conditions, cropping practices, and land use history of a specific location. The use of process-based model offers a solution for this. So the main objective of this case study was to investigate the greenhouse gas emission from the production stage, carbon debts, and carbon payback periods for cassava-based ethanol in Vietnam. The net greenhouse gas emission was calculated considering the entire life cycle of cassava-based ethanol in Vietnam. However, in this case study, I only focus on determining the emission associated with production stage, cassava production stage, emphasizing carbon stock changes due to direct land use change for cassava production for biofuel. The century models were used to quantify those changes. All the emission components were obtained from literature or calculated based on the emission factors reported in the IPCC. Due to data availability, only 4 main cassava growing regions in Vietnam were studied. These regions account for over 77% of cassava production. 4 land use types were simulated for each region, and several cropping species were used to represent each land use type. I also consider multiple cassava fresh weight yield with various fertilization application rates. Here's some main interesting finding. This I show the mean carbon debt of cassava-based ethanol versus cassava fresh weight yield. Carbon debt was strongly dependent on cassava yield. Higher cassava yield decreased carbon debt because of decreases in soil organic carbon loss. This graph shows different emission components in gram of CO2 equivalent per megajoule of ethanol. The black line here is the emission associated with direct land use change due to cassava production. And you can see that decreasing soil carbon debt reduced emission from direct land use change from around 50 to 10 gram of CO2 equivalent per megajoule. This emission constituted about 23% to 53% of the net greenhouse gas emission of cassava-based ethanol. Yeah. And the decrease in net greenhouse gas emission here corresponds to the increase of avoided greenhouse gas emission. These emissions, this is the emission avoided when replacing gasoline with ethanol. And you can see here that except for the lowest cassava yield level of 18 tons per hectare, all the simulated yield resulted in positive avoided greenhouse gas emission, meaning replacing gasoline with ethanol actually better in terms of greenhouse gas emission. These two graphs resulted in the last graph here showing the payback period of cassava-based ethanol in Vietnam. Payback period is the number of years taken for the avoided greenhouse gas due to the use of biofuels to offset the carbon debt due to the biofuels feedstock production. And you see that payback period declined with increasing in yield because of higher offset and lower carbon debt. The vertical asymptote of payback period showing the yield level at which the net greenhouse gas emission of ethanol is equal to that of gasoline, meaning the payback period reaches infinity. The vertical asymptote for cassava-based ethanol is 18.3 tons per hectare. So what does that imply? I found that carbon debt was paid off within the study time frame of 25 years, only at the cassava yield level above 33 tons per hectare. And these yield levels are only attained on farm trials and using practices that currently have low adoption rates. So this implies that research and policy should be implemented to increase the average cassava yield used for ethanol production to maximize the environmental benefits of cassava-based ethanol. And this can be done through advancement in genetic breeding, new policy to encourage the adoption of best management practices, and optimization of feedstock production and feedstock landscape design. The latter brings me to my second case study, where a biogeochemical model was coupled with GIS and optimization algorithm to identify the most efficient configuration of management practices for agricultural landscape. This case study was conducted in the irrigated corn growing area in the South Platte River Basin. And as many other agricultural regions, the basin is subject to trade-offs among food and biomass production, greenhouse gas emission, water use, and water pollution. In 2000s, South Platte River Basin ranked first in nitrate contamination and ranked second in phosphorus contamination. Water limitation is another challenge. The population of the basin is projected to increase from 3.5 million people in 2008 to 6 million people in 2050. And this will likely trigger a permanent conversion of 73,000 to 108,000 hectares of irrigated farmland to non-irrigated due to a shortage in water supply. These issues necessitate integrated assessment and better landscape design to maximize the efficiency of resource allocation and minimize the negative impact while meeting future demands. The objective of this case study is twofold. First, it aims to demonstrate the linkages between detailed quantification of ecosystem services, the inclusion of landowners' objectives, and multi-objective optimization for a rigorous trade-off analysis and agricultural ecosystem. Secondly, it aimed to optimize management practices for every cornfield in the basin, considering the trade-off between net primary production, NPP, representing the biomass production, and other ecosystem service indicators, including soil organic carbon, water use, soil greenhouse gas emission, and nitrogen leaching. Here's a quick overview of modeling approach. First, several spatial databases were acquired to create input for the basin model. Then 50 management practice scenarios were defined for exploratory simulation of the landscape with the basin, including a business and user scenario, and 49 scenarios of fertilization and irrigation. The modeling output were then optimized to create the Pareto frontiers. And here is the main finding. This figure shows the Pareto optimal trade-offs between NPP and other indicators, with NPP on the x-axis and other indicators on the y-axis. Here's organic carbon, water use, nitrogen leaching, and greenhouse gas emission. The dashed lines are Pareto frontier. And recall about the concept of Pareto frontier I presented earlier. These show the most efficient trade-off between NPP and other ecosystem service indicator. The indicator values are reported in area weighted average. The trade-off between NPP and organic carbon is win-win situation, while those between NPP and other indicators are win-lose situations. This is because increasing NPP or higher NPP production will also come with greater impacts on ecosystem. The main takeaway here is that the marginal improvement or increasing in NPP will come with exponential impacts on ecosystem. This means that over 95%, 90% of the total potential ecosystem production can be achieved with a relatively small fraction of the total potential ecosystem impact through proper management practice decisions. Here's some of the implications of this study. First, it provided several detailed maps with examples given here. The upper maps show an example of optimal configuration of fertilization and irrigation rates for the basin. The lower maps show the spatial distribution of environmental footprints. These maps can be used as a means to inform decision making, or can be used in combination with other spatial layers for more complex analysis. Now, our methodology is useful for integrated assessment, but what more important is for that to be able to use in future study. For that reason, I created the Agricultural Ecosystem Service Optimization tool, the AgEcosoft, to facilitate the adoption of this methodology in future studies. And third, although this case study focused on farmers' objective in ecosystem service trade-off analysis, in reality, there are more complex decision-making processes that involve different stakeholders. For that reason, our next step was to incorporate more tools into this, the AgEcosoft, and to consider different stakeholders. In the third case study, I integrated LCA into the AgEcosoft tool and used it to optimize the feedstock landscape design for a hybrid first and second generation biofuel production. Now, the first generation of biofuels produced from food crops like corn and sugar cane, while more commercially mature, poses several threats on food supply, biodiversity, and the consequential impact of indirect land use change on the net greenhouse gas emission. Second generation of biofuels derived from crop and forest residues or dedicated grasses could potentially solve this problem. However, they are not commercially viable yet. So combining arable crops and their residues like corn grain, and corn stover could provide a solution for large-scale and sustainable production and use of biofuels. However, this coupling required further effort to design and develop more sustainable and robust biofuel supply chain, emphasizing multiple feedstock production and management. Now, this case study focused on the Front Range Energy biorefinery, a local biofuel supply with a capacity of 40 million US gallons per year. This analysis assumed that the biorefinery can produce both first and second generation of biofuel, and the feedstock mainly came from corn grain and corn stover in the region. Corn stover is the residue that left behind after a corn grain harvest. The targeted feedstock production area is comprised of all the irrigated cornfield within a 50-mile radius surrounding the biorefinery. My main purpose was to address several questions, such as how much land should be used for feedstock production and where to produce them, how much corn grain and corn stover should be produced, what the optimum management practices are to apply for each cornfield in the chosen landscape. The problem was structured as a simultaneous minimization of production costs, farm to refinery greenhouse gas emission, and nitrogen leaching. Subject to meeting the feedstock demand for the Front Range Energy and the EPA mandated life cycle greenhouse gas emission of corn-based, or grain-based, and stover-based ethanol as compared to the gasoline. The three design objectives were calculated based on data collected from the literature and the simulated output from the AgEcosoft. They were then optimized based on a life cycle-based optimization approach to create the Pareto optimum trade-off surface. Now, to ease the visualization of the results, the color themes of objective function will be used throughout the rest of the presentation, with blue for nitrogen leaching, red for greenhouse gas, and purple for production cost. Here I show the main finding. This figure shows the Pareto optimal trade-offs among the 3 design objectives. With A is the 3D surface, perimeter surface. The red dot here are the perimeter optimal solution. Here the surface was colored with production cost here. Figure B, C, D are the projection of the 3D surface on 2D space, highlighting the trade-off between different pairs of objectives, including production cost and greenhouse gas emission, production cost and nitrogen leaching and greenhouse gas emission. The gray area here is the feasible solution, and the solid lines are the perimeter frontier. Although this figure might look a little bit complicated, the takeaway here is that the marginal decreases in production costs below $46 million per year, or in nitrogen leaching below 67 tons of nitrogen per year, or farm to refinery greenhouse gas emission below 19,000 tons of CO2 equivalent per year, came with extreme trade-offs from other design objectives. So what does this mean? From that result, here I show the refinery gate break-even price on the y-axis here, and the greenhouse gas emission footprint, nitrogen footprint on the x-axis for corn grain and corn stover. The refinery gate break-even price is the feedstock price at which the production cost of a specific feedstock is equal to its revenue, meaning the farmer breaks even. Okay. So what this informed the front range energy that, hey, your feedstock costs can be as low as $140 per dry ton of corn, about $3.5 per bushel, and $87 per dry ton of corn stover. However, you do not want to pay the farmer that price or do transaction at that price, because that will make the environmental footprint of your fuels look really bad. And you better consider the ranges I recommended here. Now on these are really interesting results. I found that the communication of such results to stakeholders and decision makers is a big challenge. Complex analysis like this could result in thousands of maps, tables, and graphs, which are difficult to present through the traditional means of communication, such as reports and scientific papers. And we need to agree that applied science is not useful if it's not reachable or it's not operational, right? For that reason, web mapping application can be used to facilitate complex and spatially